Algebra 1 Common Core, Unit 5, Section 9, Average Rate of Change. In the previous section, in 5.8, we learned about modeling linear functions, and we talked a lot about how the slope needs to be thought of as how it's a rate of change. You know, the example here was how that the slope was how the cost of airing a commercial was increasing per airing. You know, here it was, Jackson's exercise is increasing 2 minutes each day to the rate of change. And so this is really kind of going a little bit deeper into that, and it talks about that average rate of change describes the rate at which one quantity is changing with respect to something else. For that commercial example in the previous video is about how the cost of the commercial is changing per times it's aired, or Jackson is working out more each day, so minutes of workout per day kind of thing. So it's comparing two different things. Since average rate of change is a calculation of change in one thing relative to another, that's essentially what slope is, because slope is change of x over change in y, rise over run, and our slope formula, which we're very familiar with, y2 minus y1 over x2 minus x1. So that is the average rate of change. Average rate of change is slope, and that's probably the most important thing you can take away from this, that if you ever see anything asking about the rate of change or average rate of change, it's just asking you to do the slope. But what they do here is they kind of have it in a function concept a lot of times. And so in function notation, here's what your slope formula looks like. And that looks pretty different than that, but you have to remember that f of x equals y. So, instead of y2, it'd be f of x2. Instead of y1, it's f of x1, because f of x is y. So it's just a different way of writing the slope formula, but with function notations. But it still is at its core slope formula. But it's not going to ask you to do the slope between 2 points. It'll ask for what's the average rate of change over an interval. And an interval is 2 x values. So over the interval 8, 11, you have to figure out, well, 8 is the x. What is f of 8? And, this says the example on the previous page, because I cut this from my workbook, but I can't show you that because that's not the previous page of this slide here. But anyways, it worked out that 8, 7, and 11, 4 were points on the graph. So the interval of 8 and the interval of 11 had the coordinates 8, 7, and 11, 4. Again, in an interval, that's like x1 and x2. First we have to figure out the y's that go with them so that we could do the slope. So we had to find out what f of 8 was and what f of 11 was. I'll show you an example down here. So it wants to know what is the average rate of change for the given function over the given intervals. So we're going to use this graph here as our function. This is our function. And it wants the average rate of change over the interval -5, -2. So those are x values. So here's the x value of -5. And here's the x value of -2. So basically, I want to know what is the slope of this line. Now, I could just do it on the graph, but I want to show you algebraically the formula. So first, let's call this graph f of x. I should have named it, but let's call it f. So first, f of -5 is the point is -3. Right? And again, that's something that sometimes students get confused with. Why is f of 5 -3? Well, every point on this graph has a different x value. That's why it's a function. If any points had the same x value, it would not be a function. It failed the vertical line test. But every point on this graph has a different x value. This is the one point on the graph that has an x value of -5, and its y value is -3. So if I had the equation here of this weird looking function, if I plugged in a -5 for all of the x's, I would get a result of -3. And f of -2, plugging in a -2 here, x value of -2 has a y value of 1. I'm writing this as a chord. Hold on, let me rewrite this better. So f of -2, just did it again, is 1. F of -2 is 1. And what this ultimately means is we have the points -5, -3, and -2, 1. Right? Those are the endpoints of this little line segment that I want to know the slope of. And so I'm going to do the slope formula. The slope formula is y minus y over x minus x. What we see it as a lot in this notation is f of x2, which is, the y value of the second f of x and f of x1, so on. But like I said, really don't get too confused by that way the slope formula is written. It still is just slope formula. So we subtract our y values, 1 minus -3, right? Subtracting the y values. And subtract the x values, -2 minus -5. And don't forget about when you minus a negative, you get to plus a positive, right? So when these values are negative here, subtracted the x values. 1 minus -3 is 4. It becomes plus plus. -2 minus -5, these become pluses. So it's like -2 plus 5 is 3. And we can see that on the graph. This was up 4 over 3. But you might not always have a graph. You might have an equation instead of a graph, so you want to know how to do it with the slope formula. But the average rate of change for this is 4 over 3. Meaning the y value changes, the y value is increasing by 4 as the x value is increasing by 3. So this is telling me that the y is increasing faster than the x is increasing. So the rate of change is 4 over 3. Do another example from -2 to 2. Again, so that's the x value of -2, which we already know that is f of -2 is 1. We did that earlier. And f of +2 is 2, right here, 2, 0.22. So that's -2, 1, and 2, 2. Let's do my slope formula here. M equals, that'd be 2 minus 1 over 2 minus -2. 2 minus 1 is 1. 2 minus -2 is 4. So in my first example, I had an average rate of change of 4 over 3. In my second example, I have an average rate of change of 1 over 4. And looking at this graph, that makes sense that 4 over 3 is a larger number than 1 over 4. Like if I got the decimal equivalent of 4 over 3, it'd be 1.3 repeating, where this is just 0.25. This is less than 1. This is greater than 1. But I mean, look at these two slopes compared. This slope is steeper than this slope. And so it has a more steeper incline, so it has a greater rate of change. Y is increasing more rapidly on this first slope than it is on this slope. All right, and our third example here is from 2 to 5. So 2 here to 5 here. Now notice that this isn't a connected line segment. It doesn't have to be 2 points connected by a line segment. I could find the average rate of change from here to here and just find the average rate of change of that slope. It could be any 2 points on the graph. They don't have to be connected. But this is what I'm basically finding now, is the slope between those. Because what we could say is that, the graph from 2 to 5, it changes differently at different times. Like here, the slope is different than here. That's why we call it the average rate of change. Because the rate of change here is one thing, the rate of change here is another thing. But over this entire interval, the average rate of change is its straight slope from one point to the other. So we know f of 2 is 2. Yeah, I keep wanting to say f of 2 comma 2. That's definitely not the proper way to write it. F of 2 equals 2, and f of 5 equals, let's see, this was the 0.5. Oh, sorry, I don't know why that jumped. Let's see, things are starting to not work as well. Let's see, hold on, why do those, see if I can get those back over there. There we go. F of 5 is 7. Right, this is the 0.57. And so our slope formula here is 7 minus 2. Right, because this would be the 0.22. And this would be the 0.57. So 7 minus 2 is my y values, and 5 minus 2 is my x values. That's going to be 5 over 3. So the average rate of change from one spot to the other is 5 over 3. All right. The last question I want to point out here is, it simply asks, and this is a common Regents question, which interval below has the greatest average rate of change? And remember, what we're talking about, average rate of change is, kind of the slope. So we're looking for the greatest slope, which is basically saying which of these has the steepest slope. So I could find the slope over each of these intervals. But really, if you have the graph, you could see it visually. And this one, I think, is giving you all different connected intervals here. So if I want to compare these slopes here, the slope of -5 to -2, that's pretty steep, versus the slope of -2 to 2. That's definitely not steeper than the first one, so that rules out that. The slope of 2 to 4, 2 to 4, that's a flat slope. That's a slope of 0. That is a very bad rate of change. And the slope of 4 to 5. That's super steep. And you can, again, compare these slopes side by side. If you looked at this, this slope versus this slope, you see that this last one is a little bit steeper than this first one. So just visually, I could tell that this has the greatest average rate of change. And mathematically, if I were to do that, the slope of this one came out to be 4 over 3. For this one, I'll just use my graph real quick, looks like it's 1, 2, 3, 4, 5 over 1. 5 over 1. This has a decimal equivalence of about 1.3. This has a decimal equivalence of 5. You can see that 5 is definitely greater than 1.3. So this is a much steeper slope. It definitely has a greater average rate of change. All right, so it's basically just the slope formula. That's it. See ya.